proof by, I better write it, mathematical induction. I think, Graham, you might get it after just one example.
Really?
I can give you more if you want me to.
Okay.
Okay. For example, prove, thanks Bez, 2n minus 1 is n squared. 1 plus 3 plus 5 plus 2n minus 1 is n squared. So the first thing I'm going to do is think this through. 2n minus 1, is this n equals 1? It is, right?
Yeah.
I'm pretty sure actually the statement of my proof should tell me for all n in z plus, for n in z plus, which means we're starting at 1.
Okay.
1, second term, third term, etc.
Yep.
So a proof by induction always has 2 steps and then a concluding statement. So first of all, we're going to go let n equal 1. How many terms have I got on the left? Just one term. And how many terms on the right? It's correct.
Yep.
Step 1's usually easy. Not always quite as simple as that. Step 2 is the inductive step. You're going to say, let me get this right, assume true for n equals k. That is 1 plus 3 plus 2k minus 1 equals k squared. Assume that's true. For some k, that is at least 1. I need to try to prove that it's true for n equals k plus 1. i.e. That 1 plus 3 plus 2k minus 1 plus 2k plus 1 minus 1 is k plus 1 squared. See how I wrote that?
Yeah.
Take what I already had, add one more term, and it's got to equal k plus 1 squared. On my left-hand side is 1 plus 3 plus 2k minus 1 plus 2k plus 1 minus 1. And I'll get another colour. This bit is this bit.
Yeah.
I'm going to call this star, and I'm going to go, which is k squared plus 2k plus 1 minus 1 by my star. I've just done a substitution of the thing I'm assuming.
Yep.
Okay, let's, expand and simplify. K squared plus 2k plus 1 which is this.
Yeah.
Oh, wait a minute, that's k plus 1 squared.
Yeah.
Oh. Now think about what we've proven. Have a think of your tens as well, have a think. It's true for 1. If it's true for 1, then it's true for 2. If it's true for 2, then it's true for 3. If it's true for 3, it's true for 4. And on and on and on and on and on, and it's actually therefore must be true for all positive integers. Does that make sense, Ryan?
Yeah.
Does that make sense, year 10s? You will do this later, you don't have to do it yet, just yet. So we then finish with a statement that goes, this means true. If it's true for n equals k, then it's true for k plus 1. Therefore, 1 plus 3 plus 5 plus 2n minus 1 is n squared for all positive integers n by mathematical induction.
What's RTP?
Required to prove. You're about to see that a lot. So I have to prove this. I'm going, step 2 is assume it's true for k, and I'm required to prove it's true for k plus 1. And you prove it is, and then you go, well, if it's true for 1, it's true for 2, and it's true for 2, it's true for 3, and if it's true for 3, it's true for 4, and so on and so on. It must be true for all numbers, all whole numbers. You don't have to say mathematics, you can just say by induction.
Yeah.
If you don't want to write all this, you can just go, therefore, original statement is true.
Yeah.
But you need some kind of concluding statement.
Is that a mark?
Usually, yes, there's a mark for communication of what you're doing,
Okay.
which is this, and your assumed step and stuff like that.
So for the most
And if
part.
you want to, you don't have to say that. Yeah.
Yeah. For the most part, will it just be like positive integers?
Yes, but it might start from 0 or 2 or 3.
Okay.
Doesn't necessarily have to start from 1. But whatever it says you have to start from, use that as your first step.
Okay.
Is that example enough, do you think?
Can you do one more?
I think it's enough for you. I can do another one if you want.
Does it get much harder than this?
Yes, with
Okay.
more substitutions and stuff. But
Is it the same concept, just again?
exactly the same idea, just a bit more mess. I'll do another one if you want. It's not a problem.
Okay.
And then it gets harder because we then do divisibility, which is a slightly different trick.
So this is sums.
This is sums, correct.
Okay.
Your syllabus says.
Sorry, I paused it when you were going on.
Oh, okay. Which is why I don't think they can ask you this year about to prove demoivres,
Yeah.
because it's not a sum or a divisibility.
What is it?
It's a complicated, complex number expression,
Yeah.
which you can prove by induction, but it's not a sum or divisibility. So that's why I think they can't ask you this year.
Okay.
So, you want to see another example?
Yeah.
Okay, have you started that recording again?
Yeah.
Okay. Are the year 10s getting restless yet?
No.
Holy moly, here we go. Okay. Prove that the sum from r equals 1 to n of 1 over 3r minus 1, 3r plus 2 equals n over 6n plus 4 for all positive integers n. Your 10s haven't seen that symbol before, or maybe they have seen it, but not in anger. Means the sum, it's Greek sigma, the sum of this, putting r equal 1, r equals 2, r equals 3, all the way up to r equals n. And you add them all up. It's exactly like this, you just add them all together. Sorry?
I did that.
You've done that?
Yeah.
Okay. But you haven't done this proof yet?
No.
No. All positive integers n. So where are we going to start, Rain?
The first one.
Which is?
1.
Step 1. Let n equal 1. What's my sum when n equals 1? I just have a single term with r being 1. 1 over 3 minus 1, 3 plus 2. Well, that is 1 over 2 times 5, which is 1 over 10. And I'm going to say left-hand side because it's going to be easier. And right-hand side is 1 over 6 plus 4, which is 1 over 10, which is the left-hand side. See, that was a little bit more complicated than very obvious.
Yeah.
Right? Step 2. Assume true for n equals k, i.e. the sum from r equals 1 to k of 1 over 3r minus 1, 3r plus 2 equals k over 6k plus 4. I'm going to need that. Give it a name. I can refer back to you later.
Do you always know that you're going to need it?
Yes.
Okay.
When you get to divisibility, you might not want to label this one. You might do one manipulation and then label it. And we'll show you that when you get there. We'll do the sums first.
Yeah.
Okay. I have to prove true for n equals k plus 1. Okay, I have to prove, let's do this. Left-hand side will be the sum. Maybe I should write it out because then you'll see better what we're aiming for. i.e. I have to prove the sum r equals 1 up to k plus 1. 3r minus 1, 3r plus 2 equals k plus 1 over 6 k plus 1 plus 4. Because if it's true for 1, and I know it is, and if I can show it's true for 1, then it must be true for 2, and if it's true for 2, then it must be true for 3, then I can prove it for all numbers.
Does this only work with positive images?
It only works for something you can count, which means you can do this for fractions and negatives, but you can't do it for real numbers because the real numbers are uncountable, whereas the rational numbers are countable. Complicated. Okay, left-hand side is, well, I'm going to rewrite this sum by adding one term on the end. It's going to be r equals 1 to k of 1 over 3r minus 1, 3r plus 2, plus the last term at k plus 1. 1 over 3k plus 1 minus 1, 3k plus 1 plus 2. Understand what I did?
Yeah.
Took the last term out of the sum. Why? Because this is exactly what I had.
But I thought that equals n, so how can you substitute it for r?
I haven't substituted anything yet.
Like
I've taken this sum.
Yeah.
First of all, are you happy with this being what I have to prove?
Yeah.
Okay, so all I'm doing is taking this sum,
Yeah.
and I'm changing it from 1 to k plus 1 to go 1 to k,
Yeah.
and then adding on one more term, and the last term has r equal to k plus 1.
Yeah.
So I've replaced r with k plus 1. That's all I've done.
Okay.
Because this, I can substitute.
Yeah.
Okay? Watch, it's magic, it will work. That bit is k over 6k plus 4 by the star.
Yeah.
Okay? I'm going to simplify this a little bit. 3k plus 3 take 1 is 3k plus 2. And this is 3k plus 3 plus 2 is 3k plus 5. But my substitution was by the thing I knew I was going to be using. Happy?
Yeah.
What am I doing next? Some algebra. Okay, This is 2 lots of 3k plus 2, right? Maybe I'll write that because the year 10s are watching.
You know what that is?
Now I need to get a common denominator. And the common denominator is going to be 2, 3k plus 2, 3k plus 5. I am going to run out of room, which I was hoping not to do.
It's like start drawing with me.
I'll never get it off. What goes on top? K times 3k plus 5. Plus 2, in fact. You know what you have to do next?
Cancel?
Expand, collect.
Can't you just cancel the two things?
No, this is not on this one.
But it's, okay.
I'll just go back to that. It's not going to help
Yeah.
me. Expand, factorise,
Yeah.
make it look like this. Which, by the way, you might like to expand and go. Might help you work out what you're aiming for.
Yeah.
Let's expand it then. What do I got? 3k squared plus 5k plus 2 over, that is, they don't expand the bottom because we can factorise this. Okay, 3k plus 2, 3k plus 5. Having a go. I was writing it down. Okay, good. You won't need it till later, but it's fine. Okay. Factorise 2 numbers that multiply to 6 and add to 5.
6 and, 8. Add to 5?
K plus 6, K plus
Multiply to 6 and add to 5.
3 and 2.
3 and 2. So 3k squared plus 3k plus 2k plus 2. 2, 3k plus 2, 3k plus 5. 3k, k plus 1. Oh, that's nice.
Ooh, it works.
Of course it works. K plus 1 over 2, 3k plus 5 is the right hand side.
That was awesome.
Algebra. Therefore, too late to write that. Original statement is true for positive integers n by induction.